All right, it says that I am live, but I don't know if that's true. It says. All right, I believe it now. Okay. Well, I was hoping to do some problems. So today, type of problem I'm thinking of is kind of the beginning of differential equations. Though we do look at Diff-EQ a little bit in Calculus 1, I kind of wanted to think about Diff-EQ at least in the sense of um, maybe at the beginning of your class. So let's look at one and then just talk about it. So the first derivative plus the original function equals some other function. Okay. And what we're looking for is what is the original function that satisfies this equation. So this is some f of t, which we call y, and this is some df dt. Okay, this is the first derivative. And then this guy is some completely other function. Okay, this is just another function. We'll end up calling it q of t, but it's just think about it as like another function. Satisfies. All right, first time streaming, so at least on YouTube. So bear with me. We don't need this right now, so let's go. Okay, and a lot of times with Diff-EQ, it's almost like identifying a tree. So the tree kind of is just before you, right? You're looking at the tree and you go, well, it's this shape, it has these kinds of leaves, it's in this place. So I think it's this type of tree. And that's really my experience with the subject Diff-EQ is you're identifying what you're looking at. And because it's of that type, you can use this technique. Okay, so because this is a maple tree, it might have these properties. So we'll work with it in this way. Okay, so that's exactly what I'm going to do. I'm going to try to identify what type of differential equation this is. So I claim this is a first order linear differential equation. What does that mean? Well, it's first order because we're only dealing with the first derivative. So that's not so bad, right? That's not so bad. So it's not second order because it doesn't this equation doesn't deal with the second derivative. So we don't really have to deal with that. All right. Then we can claim because it's of this type, we can rewrite this. This is the first derivative plus some other function times the original function equals another function. And they're all of the same variable, right? This is the first derivative. Some function times the original function equals another function, which is of the same variable. If they have more than one variable, that's something else. We can't do that. Okay, they all have to be of the same variable. Now, if that's true, then we need to identify what are our P and what is our Q. Okay, these are the other functions. Well, in this problem, it's just the coefficient of 1. So P of t is just the number 1. And Q of t is just the right-hand side of the equation. Okay, it does appear to fit this idea. And if it does work that way, it is said that we can now find the integrating factor. Okay, so the integrating factor. So what's that? Well, here's the idea. The integrating factor mu of t is e to the integral of our p of t dt. Okay, so let's find this. So the integral of p of t, well, in our case, in this example, is just the number 1. So that is e to the t, because this is just 1. When you integrate the number 1 with respect to t, you're just going to get t. All right, so this is our integrating factor. And here's the technique to solve the equation. We are going to multiply this integrating factor times this whole equation. Okay, so let's go back to the original problem, and we're going to multiply, everybody's going to get multiplied by e to the t. So this would be e to the t y prime plus e to the t y equals t e to the negative t times e to the t plus e to the t. Okay, this is our new form. And all of this business in the middle was just to get here. Okay, so if you have practice with this and you want, you could just skip right to this point. If you identify that that's true and you're just trying to solve the problem and you can identify it, you could just skip right to this. But it takes practice to be able to do that. All right, so now that we've done all that, what does that buy us? Well, let's kind of look at where we are. So over here in this particular problem, we have e to the negative t, e to the t, and that's going to add the exponents. And when you add those exponents, the exponents would just equal 0. So you just get t times 1 plus e to the t. Okay, that's fine. E to the t y prime plus e to the t y. All right, now what do we have? On the left-hand side, I recognize something. I recognize that this is a function times a derivative plus, I'm going to call that a derivative times the original function. This is the product rule. Okay, so we have to remember from calculus class that f times g, those being two different functions, that would be f prime times g, f times g prime, right? So this is the product rule of e to the t times y. So that seems to be what's going on. We have e to the t times the first derivative of y plus e to the t times y. Now the right hand side is just the right hand side. It is what it is. But on the left hand side it looks like it's the product rule. Okay, so we identified something is happening with this product rule. I'm going to need to rewrite this problem, but that's okay. So I'm just going to rewrite it at that step. So we found that it was the product rule. And what did we find? That was um, e to the t times y prime plus e to the t y equals t plus e to the t. This is where we were. And we said, okay, well, that's product rule. I'll just call it PR here. And if that's true, and I do believe that that is true, I could say, well, that's the derivative of e to the t times y equals whatever the right-hand side is. Okay, fine, but what does that do for us? What does that actually do? Now that you've identified that this is a derivative and it equals the right-hand side, what does that buy you? Well, now I want to see what happens if I integrate this on both sides. So I'm going to rewrite this. I'm going to integrate this with respect to t, the integral of t plus e to the t dt. So both sides, I'm going to integrate with respect to t. And what does that buy me? Well, on the left-hand side, by the fundamental theorem of calculus, the integral of the derivative is just that. So it just pops out. But over here, it's going to change, right? So this t, we could take these separately because of the limit rules, and then that corresponds with the integral rules. So you could take the integrals separately, but the t has an exponent of 1, so that's going to become a 2, and then you're going to get 1 half. And then the integral of e to the t, well, the derivative of e to the t is e to the t. The integral of e to the t is e to the t. It just stays itself. And then you're going to get a big old constant right there. All right, almost done. We have e to the t times y equals this, and we're solving for y. So y equals 1 half t squared e to the negative t. We're going to divide everybody by e to the t there. And then when we divide e to the t by e to the t, that becomes a 1 plus c e to the negative t. That should do it. That should do it. Okay, so that's how I think you do it. But a lot of times with these, it has to do with identifying what you're looking at. That should do. Okay. Again, this is the first time I've ever streamed on YouTube, so I'm doing that thing where you keep looking at the stream like, is it actually working? It does seem like it's working. Okay. So that's what I think. Now, what is it that I think we found? I think we found that for given the original problem, which was y prime plus y equals t equal negative e to the negative t plus 1, y equals, or the original function would equal 1 half t squared plus 1 plus c e to the negative t. I think this function satisfies this equation, okay? And when you start with this subject, a lot of times you'll start with, here is the solution, verify that it's true. If that's the case, then you take the derivative of this and plug it into the function and show that it's true, okay? I don't know if this would help anybody, but we could try that. So dy dt, the 2 comes down, so you just get t, and the 1 goes to 0, so that's fine. And then this negative t would come down. I should say negative 1, so minus c e to the negative t. And the idea is that if you plug this in, you should get what you started with. So let's plug that in. T minus c e to the negative t plus the original function. This is also a good way to solve for that constant if you don't know what it is already. Oops. That's better. Okay. So what happens? My handwriting got kind of sloppy here. Let me rewrite this so it's at least halfway legible. 1 half plus 1 plus, there you go. That looks good. Okay, so what do we have? We have t minus this So that's going to cancel. And then you get t plus 1 half t squared. Yeah, plus 1. So you got 1 on both sides. That's going to reduce. Yeah. So that's how you would verify that that happens. Okay. That's how you verify that that occurs. But usually the class starts with that, and then it goes into this where you have to start finding the, you have to actually start finding it yourself. So if that's okay, let's look at another problem. We have another problem here somewhere. Here's one. So given y prime plus 2t y equals 2t e to the negative t squared. We want to find, I mean, I don't want to say solve for y, but in a way, that's what we're doing, right? So, kind of in a way, it reminds me of um, algebra. I mean, you're solving for a function, you're not solving for a variable, but it's kind of in that way. So, we have the first derivative, that's fine. We have this as the original function, whatever that may be, and then we have some other function here. Again, my analogy with trees is kind of silly, but it's not too far off. So we're going to identify this as a first order differential equation. And I would say in that case, we can say, well, it does seem to have that structure. So our P of t is 2t, and our Q of t is 2t e to the negative t squared. That's the idea, okay? And that's coming from y prime plus P of t times y equals some Q of t. Everybody has to be in the same variable. I mean, t is what we usually think of, but I guess it could be x or anything. But it has to be the same variable, otherwise, that's something completely different. Okay. If that's the case, and it does appear to be so, then we can find our integrating factor. And our integrating factor is yet another function, and it's e to the integral of whatever pt is, p of t. So this is e, and then that's 2t dt. Okay, so what's that? So 2t, the t is going to get squared, and then it's going to get 1 halved, right? Times 1 half. So that's going to be 1 half times 2, which is 1t squared. Okay, that looks good. Now we're going to multiply this times the original function. Okay, everyone's going to get multiplied by that. So what happens there? Well, in that case, you'd have e to the t squared y prime plus 2t y e to the t squared equals 2t e to the negative t squared, that's the original, times e to the t squared. Well, on the right hand side, I'm noticing I have e to the negative t squared, positive e to the t squared. When you add those, that's just going to equal 0. So that's e to the 0. So that's 2t. And then over here, let's notice what's going on the left-hand side. On the left-hand side, you have e to the t squared y prime, then 2t y e to the t squared. So if you look at this, you see, well, look at that. That's the product rule. That's the product rule. That's a function times another function equals f prime g f times g prime. That's the product rule. So if that's the product rule, I can rewrite it as the derivative. So that means this is d dt e to the t squared times y. And that condenses that quite a bit. We noticed that when you add these exponents together, since it's being multiplied, that'd go to 0. And then it just leaves us with 2t. All right, so I think we're almost done with this problem. We just have to finish it up now. All right, I'm going to take this away. And now that we are here, what will happen? We have d dt e to the t squared times y equals 2t. What do you do now? Now I think we could integrate both sides with respect to t and find what that y has to equal. So the integral of d dt e t squared y equals, whoops, it's not quite right, dt equals the integral of 2t with respect to t. So by the fundamental theorem of calculus, the derivative is being integrated with the same variable, so it's just going to pop out. So that's pretty cool. What about this right-hand side? We have 2t, so the t is going to get squared, and we're going to cut it in half, right? And half of 2 is 1, so this is going to become t squared plus some constant c, and now we can solve for y. So this implies that y equals t squared e to the negative t squared plus c e to the negative t squared. Is there anything else we could do to clean this up? Maybe. I don't know. I don't know if I see anything else to do. I guess we could factor out that e to the t. If we factored this out, and this is up to you how you like it, but you'd have t squared plus c. I guess it's a little cleaner. So that's what I think. Now, what is that? That's a function. So I think that's what y equals, and that's what I think satisfies the original problem. So I think that would be the function that would satisfy it. And c would depend on where this whole thing started, right? So given, what was the original problem? I have it written down here somewhere. So given y prime 2t y 2t e to the negative t squared, I think y equals e to the negative t squared plus some constant. Okay. That's what I think. Well, I wonder if we have time for another problem. Do you have another problem written down here that we could work on? Let's try this one. So given 1 plus t squared y prime plus 4t y equals 1 plus t squared to the negative 2. Okay, we're going to try to solve for what is the function that satisfies this. And so far, how we've done that is just by identifying the type of problem we're dealing with. So this is not the same as the other problems that we dealt with. I think the first step we should do to try to get it to be that is I'm going to divide everybody by this 1 plus t squared. So if I do that, I would have y prime plus 4t divided by 1 plus t squared times y equals 1 plus t squared to the negative 2, 1 plus t squared. So in that case, this looks like if it was already to the negative 2 from the original problem, you're dividing by another one. So that seems like that would be to the negative third to me. So I wonder if I could write it that way. Okay. This is supposed to be a y. It kind of looks like something else. Now, are we in good shape from here? So I think our p of t would equal 4t 1 plus t squared. Our q of t would equal 1 plus t squared to the negative third. Okay. And that's coming from y prime p of t y equals q of t. It does seem like that works. Well, this one's a little bit uglier than what we did last time. So now we have to find the integrating factor. Okay. The integrating factor in this case is this, which is p of t dt. So I need to find what's this. Okay, so let's find what that is. That's 4t 1 plus t squared dt. Well, you could think substitution. Think you could do substitution if it was um if this was u 1 plus t squared du would equal 2t dt, and we have 4t, so you could just double it, and that would be 1 over u, which is the natural log. So that doesn't look too bad to me. So I think we could say that's 2 times the natural log of 1 plus t squared. And that's going to be oh, I should be careful. That will be in the exponent of that e there. All right. So I think that implies that we have e to the natural log of 1 plus t squared squared. Okay. But this is e to the natural log. So this actually, we're going to lose the e altogether. And you're just going to get 1 plus t squared squared. Okay, that's what I think our integrating factor is. And now we need to multiply everybody by that. And then that will send us on our way. Okay. So if I multiply everybody by that, that's 1 plus t squared squared times y prime. And then we'll have 1 plus t squared squared 4t 1 plus t squared y equals 1 plus t squared squared times 1 plus t squared to the negative third. And that's going to be -1. So then we get, so messy, but you got to do all the algebra too. 1 plus t squared squared y prime plus, this is just going to cancel, 4t 1 y equals 1 plus t squared to the negative first. So that's where I think we are at this point. Okay, so I'm going to have to clean things up a little bit, but we're moving right along. Okay, so where are we at? We're at 1 plus t squared squared y prime plus 4t y equals 1 plus t squared to the negative first. So from there, what can we do? Well, first off, I think that was a mistake. That should be to the first. Yeah, that's better. Now, if we multiplied everybody by 1 plus t squared, we would no longer have to deal with this -1, and that could be helpful. But I don't know. It's a guess. A lot of times what we're doing is we're looking to see how this could be the product rule. Is that true? So in the previous problems, we found this is either the product rule or it is not. Let's see if it is. You're going to have to chain rule, so the derivative of 1 plus t squared, and I gotta be so careful. Now it is squared. So the 2 would come down, and then you would get 2t. 2t times 2 is 4t, and this is the product rule. Okay, so this is the product rule of this. So I can rewrite it. This is d dt 4t 1 plus t squared y equals 1. All right. Now, if we do the integral on both sides, that relationship should still hold true. And this is just going to pop out, and then we can solve for y. Luckily, I don't have to actually solve this. It would be horrendous if I did, but I don't. Okay. And I'm wondering, actually, you know what? I think I chose the wrong thing. That's not quite right. That should be 1 plus t squared squared times y. That's right. And then you take the derivative and you get this. Right. Okay. So now we have it. So that becomes what it is because of the fundamental theorem of calculus. And then that's going to be just t plus c. So we're almost done with this problem. Okay. So that means we have 1 plus t squared squared y equals t plus c. And so from there, we can solve for y, and we'll say that y equals t divided by 1 plus t squared squared plus c times 1 plus t squared to the negative 2. That should do it. That should solve that differential equation. Okay. All right. So it is kind of just identifying the type of problem that you're looking at. If you can identify it, from there, you can say, well, um, it's this type of problem and I know how to work on it. It kind of seems strange in math. A lot of times we work on it to find the solution, but here you have to identify the type of problem you're thinking of, and then you can use this technique. So I think that's maybe a good place to stop this first live stream now that we've just had some experience of looking at these